Hey everyone, Paul DeLuigi here, and we're back again with another video presentation for you. This week's Unit 2 presentation will be on gene mapping, and in order to demonstrate this concept, I have made a PowerPoint which you will follow along with. So let me open up our PowerPoint. Here's our title page, our mapping demonstration for our genetics class by Dr. Michael Shea. And this is our given data set. You can see it is a number of genes and their offspring ratios. Now, if we add up all the offspring ratios, we have come to the total of 5,742 pairs. Coming down. So the first step in this problem is to determine the grouping and crossover categories. The easiest way to accomplish this is to look at our data set and see which groupings are similar. So down here I have categorized them into our non-crossover group, our single crossover group, and our double crossover groups. And we can see that the offspring ratios match up with the ABC and the +++ sequences, and same with our single crossover groups and then our double crossover group with these similar ratios. Now, the best way to determine the actual gene arrangement is to assign a probability to each grouping. Here we have the ABC grouping or probability, and then we switch the sequence so that C is in the middle in this next probability, and then our third probability we have switched the sequence down here with A in the middle. And again, our original sequences. So what we are looking for, if we come down here to our double crossover group, this sequence right here, the A++ sequence. Now, which probability is most similar to the A++ sequence down here with our double crossover group? So if we come up top here, so we see we have, what we're looking for is this triangular sequence here, plus B plus. We come down here, we have A++. Probability number 2, we have plus C plus, and again, that does not match. So in our third probability, we have A in the middle of the sequence, and then again, A++, and then if we come back to our triangular pattern, it matches. We have an A++. It's not the exact same sequence, but that doesn't matter because when we come over here to our actual arrangement grouping, we will adjust the sequences to match the probability which matched our double crossover sequence down here. So the new actual arrangement is BAC, and then we, again, with our second grouping here of our single crossover group, 2 groupings, we're going to switch the A for the B, and then we're going to switch the plus for the A. And this gives us our actual sequencing arrangements. In our next slide, we will determine the distances between the genes. So in order to accomplish this, we are going to total our offspring ratios, and we will get the sum of 2,702. And we take that and divide it by our total offspring ratio, and we come up with a percentage after you times it by 100. And we have done that for our single crossover groups and then our double crossover groups. So down here we know that the sequence is BAC. What we don't know is the distance. So in order to determine the actual distance between the genes B and A, we are going to come to our single crossover grouping here. And then we're going to look at our sequence B to A, and then in this single crossover group we're going to look at A to C. And we all know that, as stated before, our sequence is B, A, C. So we are going to assign this distance in accordance to our groupings. So down here we have our total of the single crossover group. We have 14.3, and then our double crossover group of 4.2. Adding these two numbers together will equal out to be 18.5. And then over here from A to C, we have our 34.5 plus, again, we're going to use our double crossover group to determine this distance. Now we will calculate the coefficients of coincidence. In order to do this, we are going to use the observed double crossovers, and we are going to it's going to be divided by our expected crossovers. Now our expected crossovers, we need our map distances again, and we can see here we have our 38.7 and our 18.5 again. Now, in order to determine the double or the expected double crossover groupings, we need to convert this to decimal form. And we see we have just basically taken out the step of multiplying by 100 and leaving it at the decimal form. And so we will multiply 0.387 times 0.185 equals 0.071. Now times that by 100 and we get our 7.1, which we will then use with our observed double crossover events to be divided by that number, and we will equal, it comes out to 0.591. Now the next step in the problem is to calculate the interference, and we are going to just simply take 1 and minus our number of expected, and it equals out to be 0.409, and that is our calculated interference. So the conclusion from this problem is concluded that there is a positive interference because we came out with a positive number. We had 40.9% less double crossovers than expected. And now we can double check this by just simply reversing our equation and dividing, which equals 0.591, which we got up here in our last slide, and then times and then minus by 1, which gives us our 40.9. And again, this is our interference number. So all the mathematics equals up, and so we have solved our sequencing problem. So thanks again, thanks for watching, and we will see you on the next one. Thank you. Bye.